It's interesting that I think for this session, the topics are all about testing. I mean, each paper is about testing. So it's great. For my previous session, the topics are really diverse. Okay, I think we can start this session now. So hello, everyone. I'm Xie Zhang. I'm currently a research fellow at University College London. It's my great pleasure to chair this testing and analysis session. And we have 5 talks. Each talk will be 5 minutes long. So we will let each speaker give that talk one by one. And after all these talks, we will then have the Q&A session. So if the audience have any questions, anytime, please post your questions in the chat window. Yeah, so I think we just go to the first talk from Trinity Steven. No, sorry if I pronounce your name.
No problem. Yeah.
Yeah.
Thank you.
Yeah, please go ahead.
So I'm Quentin Stevener. I'm from the Vrije Universiteit Brussels in Belgium, and so let me. Okay. So this is a paper about. Can you see the screen first? Maybe just make sure. Yeah.
Yes, we can see.
So this paper is about slicing WebAssembly, and that's research done in collaboration with Dave and with Koen. And so this paper is about WebAssembly, and WebAssembly is this new binary format for applications that basically you can take an application written in a high-level language, compile it to WebAssembly, and execute it, for example, in web browsers. And so what you can do with WebAssembly, for example, is build an application like what Google Earth is doing, where you have pieces of the application that is written in JavaScript to do like user interface, and then the more heavy computations are offloaded to WebAssembly. And if you look at how WebAssembly has been used in the past, some of its uses were malicious. So as you visited malicious web pages, it would give you a WebAssembly program to execute that would, for example, mine cryptocurrencies behind your back. So we need tools to be able to reverse engineer these WebAssembly programs. And so for that, what we propose is a program slicing approach. And so what is program slicing? The idea is that it's basically a technique to minimize a program according to a slicing criterion. So here we have a C program where we compute a sum and a product, but suppose we are only interested in the behavior of the highlighted line. And so that line is what we call the slicing criterion. And the slicing technique will provide us with the minimal version of the program that preserves the semantics for that line. And so basically we want to apply this to WebAssembly. First, we'll look a bit at WebAssembly and execute a program by hand, and we'll look at what we call the WebAssembly validation requirement. So WebAssembly is a stack-based language, so we'll visualize the stack as we execute the program. So in the first instruction, we access the argument to the function that we execute, and we push it on the stack, so we have one value on the stack. Then we have an if instruction that pops the value from the stack, and then, for example, it will go into the then branch. Then we have a few more instructions that push more values. We have an addition that takes the two top values from the stack, add them together, and push the result on the stack. Then, for example, we have a function call that takes one value from the stack, computes something with it, and pushes one result on the stack, and then we drop this final value. So what the validation requirement tells us is that, for example, both of the branches of the if should agree in terms of stack layout. So because here we have an empty stack at the end of this branch, in the else branch, which is empty, we also have an empty stack, so that's a valid WebAssembly program. So now if we try to compute a slice with this instruction as the slicing criterion, so we can try to do that for WebAssembly using regular slicing approaches. So to do that, we'll simply follow the dependencies. And so here, to add two values, we need the values on the stack, so we need the two previous instructions. For these three instructions to be executed, we need the if statement. And for this if to execute, we also need the condition. So that gives us what we call a closure slice. And so that should preserve the semantics for the add instruction. The problem is that if we try to execute this program, there's a validation error because we have left one value too much on the stack. And more problematic, if we try to load this program into a WebAssembly analyzer, this is not a valid program, so it cannot be loaded. And so in this paper, we provide a slicing approach that works in 3 phases to be able to produce valid WebAssembly slices or executable slices. So you can look at the details in the paper and in the full presentation, but the idea is that we first compute a closure slice, as I explained. And so this gives us a slice that may not be executable. And then we work locally on the instructions that have been removed to add some dummy instruction that will manage to preserve the stack layout. And by the end, we have an executable slice. So you can find the implementation online. There's an artifact, and we have evaluated it. So for reasons of time, I will focus very quickly on some part of the evaluation. So we have basically computed almost 500 million sizes with our implementation, and the slice sizes are around 52-53% of the original program, and that's actually lower than related work on slicing assembly code. And the slices are computed quite quickly, so within a few seconds. And so that's all on real-world data. So to sum up, we have a 3-phase approach to compute executable slices. We have implemented it and evaluated it, and so the implementation is freely available online.
Okay, thank you very much. So our next talk is about automated assertion generation via information retrieval and its integration with deep learning. The speaker is Hao Yu from Peking University, China.
Okay, thanks for your introduction. Hello, everyone. I'm Hao, a second-year PhD student from Peking University. And the title of our work is Automated Assertion Generation via Information Retrieval and its integration with deep learning. This work was done in cooperation with Peking University, Purdue University, and the Huawei company. I first introduced the background of assertion. Assertion is used to validate the correctness of methods. Here is an example of a test method with an assertion. The place cycled by the red box is the assertion, which is used to judge whether the implementation of the getName method is correct. In recent years, based on other already written unit tests, Atlas takes a test method without any assertion along with its focal method to output an assertion. And the figure shows an example of the input and the output of Atlas. The input of Atlas contains focal method and test method. The focal method refers to the method under test. There are 2 major limitations of Atlas. First, assertions generated by Atlas are not explainable due to the unexplainable nature of deep learning. Second, the effectiveness of Atlas is poor. These limitations, we propose our approach. Our approach includes an R-based approach and an integration approach. The R-based approach contains 2 techniques, R-based assertion retrieval and retrieval assertion adaptation. Here are the IRAR and the example of IRAR. We short IR-based assertion retrieval as IRAR. To generate an assertion for an input focal plot test in the left figure. IRAR compares it with each focal plot test method in the training set. Find the most similar one as shown in the right figure, and return its corresponding assertion. Next, I introduce the RA-adapt technique. We propose an automated adaptation technique, RA-adapt, to modify a retrieved assertion toward the correct one based on context information. RA-adapt first decides whether the assertion should be modified. RA-adapt considers an assertion necessary for adaptation if it contains at least 1 token absent from the input focal plot test method. Then RA-adapt decides which token should be modified. RA-adapt considers token that is absent from the input focal processor method as a candidate token for modification. Finally, IRDEP decides what value a candidate token should be replaced with. For this step, we design two replacement strategies to decide the replacement value. One is based on heuristic, and another is based on neural networks. Then I introduce the integration approach. We propose an integration approach based on a capability inference model, which calculates the capability between the retrieved assertion and the current focal processor methods. Then I introduce the evaluation. We conduct experiments to answer the following research questions. Table 2 shows the RAR technique substantially outperforms the compared deep learning approach Atlas. Table 4 shows the RAR could consistently outperform the Atlas on all the assertion types, and Table 5 shows the similarity coefficients have little impact on the effectiveness of RAR. Then I introduced the RQ2. Column 3 and column 4 in Table 2 show that both adaptation techniques can substantially improve RAR, and RA-adapt-NN can achieve higher improvement than RA-adapt-H. Next I introduce RQ3. The last column in Table 2 shows that the integration approach consistently outperforms the DR-based approach and the IR-based approach. Finally, I conclude our work. We have made the first attempt to leverage the information retrieval to assertion generation and propose an IR-based approach, including the technique of IR-AR and the technique of IR-adapt. We also propose an integration approach, and the experimental results demonstrate the effectiveness of our approach. That's all. Thank you.
Okay, thanks for the talk. So our next talk will from Huayao Wu, Nanjing University, China, to talk about combinational testing on RESTful APIs.
Okay, thank you. And hello, everyone. I'm Huayao Wu from Nanjing University. And my talk today is about the use of combinatorial testing technique to test RESTful APIs. REST is a popular architecture style for creating web APIs and has been widely used to build modern web services. And currently, web developers usually use the OpenAPI or Swagger specification to document such RESTful APIs. And in the specification, we can find the detailed information about the operations that can be performed and the input parameters of each operation. These operations and their input parameters clearly constitute a huge and constrained input space. This test scenario is like system testing, and to generate a test case for RESTful APIs, we need to determine not only the execution orders of these different operations, but also the value assignment of input parameters of each operation. To this end, in this study, we proposed a systematic and automatic approach named REST-AT to test RESTful APIs. REST-AT is systematic because it uses combinatorial testing to generate test cases, which can cover and test the interactions of a certain number of operations and also the interactions of input parameters. REST-AT is also automatic as its complete testing process is fully automated. This includes the creation of test models of combinatorial testing, which should usually be performed by human testers. This picture gives the overall workflow of the REST-AT approach. Giving a Swagger specification as the input, REST-AT will first consider the input space of operations and then generate a sequence covering array to determine the execution orders of these operations. The key problem here is to determine the dependency relationships between different operations. And in REST-AT, we the layer relations of resources and the CRUD semantics to determine whether a sequence of T operations is constraint satisfying or not. REST-AT will then use a classic gradient algorithm framework to generate a set of operation sequences to cover the combinations of any T operations. This algorithm will generate an operation sequence to cover the most previously uncovered T-way sequences at each time, and repeat until all T-way sequences are covered. Once the set of operation sequences can be obtained, REST-AT will then consider the input space of each operation to determine the concrete input parameter values to execute each operation. In this phase, a key problem is to identify the value domains for each input parameter. In REST-AT, we used several heuristic strategies to determine the candidate values for each parameter, which takes both runtime, domain-specific, and history information into account. Another key problem here is the extraction of constraints from the natural language descriptions in the specification. In REST-AT, we use natural language processing to implement a pattern-based approach so that the formal representation of constraints can be automatically extracted based on a set of predefined patterns. Finally, REST-AT will use an adaptive strategy to generate concrete HTTP requests. The basic idea is to test the required input parameters first to ensure the successful execution of the operation, and then add optional parameters into the test model to exercise more service behaviors. In the experiments, we posed 2 research questions, and we used 2 popular real-world web services, GitLab and Bing Maps, as subject APIs and a test. In the first research question, we compared the performance of REST-AT against an existing state-of-the-art testing tool named Restler. And according to the experimental results, we found that REST-AT can test more operations and find more bugs than the Restler tool. And also, REST-AT runs faster than the existing tool. In the second research question, we investigate the impact of the different coverage strengths applied on the performance of REST-AT. And we found that the coverage strength of operation sequences tends to have a greater impact, and the coverage strength 2 tends to be the best choice. And okay, that's all for my talk. Thanks very much.
Thanks, Huayao. So next speaker is Yinquan Zhao from Tianjin University, China. So their work is titled History-Driven Test Program Synthesis for JVM Testing. Please go ahead, Yinquan.
Okay, thank you. Hello, everyone. I'm Yinquan Zhao from Tianjin University. In this presentation, I will introduce our work of history-driven test program synthesis for JVM testing. The goal of this paper is to generate bug-revealing test programs as much as possible. To achieve this goal, we further explore the historical bug-revealing test programs, since we think this test program contains the ingredients facilitating the detection of the bug, involving complicated code logical or cover corner cases. And we utilize program synthesis to generate new synthesized test programs by combining the ingredients extracted from various historical bug-revealing test programs and put these ingredients into different contexts. Finally, we execute the synthesized test program to cover more interested JVM's behaviors and thus to detecting new bugs. However, to achieve this goal, there are 2 main challenges remain to be addressed. The first challenge is how to measure and extract the ingredients in historical bug-revealing test programs. And the second is how to guarantee that the synthesized test program is valid. To address the 2 above challenges, we propose Java-Tailor. Java-Tailor first initialize the seed programs from to form a seed pool at step 1 and extract code ingredients from historical test program to form an ingredient pool at step 2. Then it randomly selects an ingredient and seed in step 3 and step 4 and synthesize them together in step 5 to generate a new test program. Finally, Java Tailor uses this synthesized test program to differentially test JVMs. If there are inconsistencies in the output of these JVMs, we output the difference report and the following synthesized test program. Otherwise, we put the test program into the seed pool for further synthesis. In particular, Java Tailor solves the two challenges in step 2 and step 5. In the following, I will introduce the 2 steps. To make a trade-off between extraction efficiency and effectiveness, we design 5 types of code ingredients based on block granularity. To conduct ingredient extraction, Java Tailor first transforms a test program into a control flow graph based on the Jimpo code and showing in the right. Then it analyzes each code block from top to bottom and records the code ingredients that meet the predefined requirements. For example, based on this control flow graph, we can extract 4 ingredients. After this process was done, an ingredient pool can be built by Java Tailor. The second challenge is to ensure that the synthesized test program is valid. Since the original syntactic and semantic constraints of the ingredient may be broken during the synthesize process. For example, if we insert the ingredient composed of line 5 and line 6 in the historical test program into a new seed program without any change, the synthesized test program must be invalid since it missing some variable definitions. And if the invoked function getCount at line 5 is a protected function, there is also no definition of this function in the synthesized test program. To ensure that the synthesized test program is valid, we design several strategies to fix the broken constraints. For the variable missing its definition in the ingredient, Java Tailor prefers to find whether there is a variable in the seed program that can be used to replace the variable in the ingredient that is type compatible variables. If such variables are found, Java Tailor replaces the variable in the ingredient with the identified type compatible variable in the seed program. Otherwise, Java Tailor constructs new definitions for those variables. And in this way, we can make the interaction between the ingredient and the seed program stronger. For the missing or API definitions, Java Tailor fixes this broken constraint by changing all the private or protected function involved in the ingredient to public. Based on the fixing strategies in Java Tailor, the synthesized test program in the previous example could be like this, where the Java Tailor reuses the variable str at line 4 and creates new variables for usage, count, and mn at line 5, 6, and 7. Finally, a valid synthesized test program can be generated. Then Java Tailor executes it to check whether it can reveal the JVM bug or not. To evaluate Java Tailor, we adopt 2 popular JVMs, that is Hotspot and OpenJ9. And we can collect the test programs revealing historical bugs from the Hotspot test suite. And the experimental results demonstrate that Java Tailor can outperform than the state-of-the-art technique class_bin. That is, Java Tailor can achieve higher JVM code coverage and expose more unique inconsistencies. Moreover, Java Tailor has found 6 unknown bugs, and these bugs have been fixed by developers. That's all. Thank you.
Thank you very much. So our last talk in this session will from Marcel Bockme from Max Planck Institute for Security and Privacy in Germany. So he will talk about the reliability of coverage-based fuzzer benchmarking.
Yes, hello. That's correct. My name is Marcel Böhme of the Max Planck Institute for Security and Privacy, and I'll talk about our paper on the reliability of coverage-based fuzzer benchmarking. And this is in collaboration with Laszlo and Jonathan at Google, who also built the FuzzBench platform, a fuzzer benchmarking evaluation platform. So the question that we start with is, suppose you have a couple of fuzzers and none of those fuzzers find any bugs in your program. How do we know which fuzzer has the biggest potential of finding bugs, right? So you have fuzzers and none of those find any bugs. Which fuzzer is better? And so often the answer is, if you ask anyone in practice and anyone in research, well, we measure the coverage of the test suite that the fuzzer generates. We measure code coverage, right? And the key idea of this measuring code coverage is you cannot find bugs in code that is not covered. Very simple. A problem with this, a problem with creating fuzzers is that even a fuzzer that doesn't do anything finds no bugs, right? And that's why we use fuzzer. That's why we use coverage as a proxy measure. But many people then, maybe since the 80s, investigated theoretically how coverage is actually related to bug finding. And maybe since the 90s, we also looked at this empirically. And there are many studies on this. And some find strong correlations. Others say there's no strong correlation. There's a reason. There's an ICSI paper 2014 which says there's no correlation if you take test suite size into account. And there are some follow-up works which say that this is incorrect too. But in any case, what we do is we rerun this experiment and investigate how strong this relationship actually is. And we find a very strong correlation. So this is the average branches covered on this side, and this is the number of bugs found. And we almost see straight lines, which indicates strong correlation. So we find as a fuzzer covers more code, it also finds more bugs. So that's awesome. So, but the problem is that fuzzing folks are not really convinced by that. You can't just use coverage and then make conclusions about the bug finding of our fuzzer. We cannot compare two or more fuzzers in terms of coverage in order to establish one is the best fuzzer in terms of bug finding. And what they do is, when they claim this in the CCS 18 paper, which is the authoritative paper on fuzzer evaluation these days, is they cite this paper that says there's no strong correlation. But maybe the question is not about correlation, but about something else, which we call agreement. And in fact, people in statistics looked at different statistical problems and say that there's a common pitfall. You should sometimes use agreement. And so what is agreement? So suppose you have two instruments, and these two instruments measure the acidity of the liquid in some vials. So a strong correlation means both instruments indicate a higher level of acidity as the acidity in ground truth actually increases. So as the ground truth acidity increases, both instruments also show an increase in pH values. But agreement means you have two instruments and you have several tubes, and you measure and you rank these tubes. You rank these tubes according to the acidity. That these ranks might be different, so they might be differently ranked. And this is a weak agreement. Both instruments do not always agree on which one is better. So here's a ranking of fuzzers in terms of coverage and a ranking of fuzzers in terms of number of bugs found. And if we compare this ranking, we see almost a random scatter, right? So here's one case where we have the worst fuzzer in terms of coverage being the best fuzzer in terms of bug finding, right? So even though we have the strong correlation for one fuzzer, we only see a moderate agreement when we compare two or more fuzzers. So there's a moderate agreement. This means you cannot reliably substitute one instrument for the other. So in summary, we observe a moderate agreement on superiority or ranking. We also investigate threats to validity, and only if we require differences in coverage and bug finding to be highly statistically significant. So highly statistically significant means 0.0001 as a p-value. We observe a strong agreement, but there are also some caveats to that. And we explore these pitfalls of bug-based benchmarking as well. So we discuss coverage-based benchmarking in the paper, but we also explore problems of bug-based benchmarking, and we make recommendations for sound fuzz evaluation. And so the key conclusion is you can substitute coverage for bug finding, but only with moderate reliability. And so what is the larger lesson of this? I think in our community, we need more training in terms of statistics. And in our community, we should also discuss and investigate our experimental design, our study design, and think about soundness of these studies that we have. Thank you.
So now we will enter the Q&A part. So I see that in the chat window, there is a question for Hao Yu, and he already answered that. So we have a question for Hua Yao. Could you learn some constraints during testing, or the part of inferring constraints is done only statistically at the beginning from the Swagger spec? Thanks.
Hello, thanks for the question. And in our approach, we do not learn constraints during the testing process. The constraints between operations are analyzed and extracted based on the Swagger specification itself. And for the constraints between input parameters, and we use a pattern-based approach, and the pattern must be predefined. And so all these stuffs are predetermined to make our test approach work. And that's a good idea that we can learn the constraints between during the testing process, and we can, of course, we can establish a feedback-driven approach to make the testing more effective. And okay, that's my answer.
Thanks. I think for another question for you, Hua Yao, did you consider, or will you consider in the future, the possibility of modeling malicious interactions? For example, having a attacker that does not follow the input specification.
Okay, thanks. Seems a good point, but currently we do not work on that direction. And nevertheless, I think that's a good idea to model the malicious behaviors.
Yeah. Thanks. So we have a question for Marcel. In other testing communities, such as search-based software testing, mutation score is a popular evaluation metric since it may be a better indicator for bug finding capabilities compared to coverage. Do you have any insights on why this hasn't been adopted to fuzzing evaluations yet? Interesting question.
So I have several answers for that. So the first is the actual answer, and then I'll talk a little bit about mutation testing and bug finding. So the answer about why this has been adopted in fuzzing is because often, so in fuzzing, one of the main concerns is performance. So you want to do things very fast, and performance is also the main, and scalability is also the main caveat of mutation-based testing. So you have to generate all these synthetic bugs, and then you evaluate how good the fuzzer is in terms of killing these bugs, right? And since in fuzzing we are using really large programs, there are also a lot of potential mutants that you can generate, that you have to generate, and so performance might be a problem. But what mutation testing addresses in fuzzing is coverage is only about reaching a certain place. Mutation analysis helps us identify ways how things that you reach also propagate. So if you have an error, if you inject an error, you can also measure how this error propagates to, let's say, to a crash location. And so this propagation is something which you cannot measure with coverage, but you could with mutation analysis. So there's definitely going to be some research, and I've seen some discussions on Twitter about using mutation testing. And then secondly, so what we introduce in this work is we introduce a way of evaluating fuzzers, evaluating measures of proxy measures of bug finding. So one proxy measure that we investigate is branch coverage versus bug finding, but mutation and mutation testing, mutation adequacy versus bug finding is something which we also hope to see in the future, and particularly not using a correlation but agreement, which is the methodology that we propose here. So I'm looking forward to these kind of investigations.
Yeah, thanks for the answer. Yes, I also have a question for you. So you study the correlation between bug detection and coverage for the fuzzers. So I wonder where your bugs come from, because I feel that the distribution of the bugs actually matter a lot. Imagine that if the bugs come from particular lines that are not covered, if the bugs focus on those lines, then the correlation you observed might be small, right?
So we have.
So how do you guarantee like the bugs like distribute evenly and yeah, like threats like that? Thanks.
So we have an entire section on on caveats of bug-based benchmarking, and so a study design that is very common in this correlation studies is that you, instead of using real errors, you use mutations, and then the assumption is that mutations are proxies for actual fault detection. But then another more recent kind of way of benchmarking fuzzers is using real errors that exist in real systems. There's the Magma benchmark, the other similar benchmarks. Fuzzbench was also designed in the beginning with actual errors in mind. The problem with this ground truth-based benchmarking is that you're subject to several biases. One bias is survivorship bias. So survivorship bias means bugs that were earlier identified, for instance, by AFL or libfuzzer, and become part of the ground truth. Of course, on these bugs, AFL or libfuzzer will perform better. Then on the other hand, if you have ground truth bugs and you have fuzzers that perform very well in detecting unknown bugs, those fuzzers might appear to perform worse, right? Because we're only measuring with respect to these ground truth bugs that we know how to find. We do not measure how to find, how well the fuzzer performs in finding bugs that we do not know how to find. That's one thing. So what we do is, in order to circumvent all of these threats to validity, we use a post hoc bug identification approach. Post hoc means we run all these fuzzers on random programs and then use a deduplication method, first automatic, then manual, to identify which bug each fuzzer finds. So we do not choose. So what we do is we choose programs because they were historically more likely to contain bugs, but we do not focus on specific bugs or anything. They kind of emerge of this study.
Thanks. Do we have more questions from the audience? If not, I have a question from. I have a question for Chanting. So because you work on slicing of Webassembly, which is interesting because it's not on the original source code. So I wonder whether the slicing results might be difficult to understand for developers. I mean, the interpretability of your results, how good it is. Have you done any exploration on that?
So in the paper, the data set that we evaluate this approach on is a set of binaries for which you don't have access to the source code. So in that sense, you have, the best you can do is analyze the binary, but we also evaluated the slicer on C programs that we compiled to WebAssembly. And so we compile the C programs to WebAssembly, we slice this, and we compare that to slicing the C program and compiling the slice to WebAssembly. And so what we noticed is that, the slice is smaller, and sometimes smaller in the case of the compiled C slice, but it's often, you have like the compiler can add some more optimizations because the code is simpler, and so you kind of lose some information with respect to the original binary. So you might have slightly different behavior there. So slicing at the level of the binaries is preserving more what happens at the execution, at least.
Yeah, thanks. So have you talked about developers, like what their views are for the slicing results that you provide?
No, so our interest was to do some kind of reverse engineering and to simplify some functions in WebAssembly to be able to analyze them. We haven't tried it on like giving it to developers and see what they think about the slice. We only have looked at it manually ourselves.
Thanks. So probably a related question to this, like, do you have any plans on further downstream tasks of your slicing results?
So
Like,
yeah, so now we have the slicer. There are still some things to improve, like it's intra-procedural. We can go inter-procedural. That will be more interesting. And one of the idea initially was to be able to develop program analysis for WebAssembly, but because WebAssembly is this binary language where you can have a function that is millions of instructions long, it's quite difficult to do some heavyweight program analysis on that. So if we can slice the program or the function to analyze, then we can maybe have better scalability in the analysis. So that was the initial goal. And so that's something we have to investigate now.
yeah, thanks. So we have some questions from the chat window. First one is for Marcel. The correlation between code coverage and bug fighting capability has been long discussed in general, not for fuzzers. I mean, for measuring the quality of manual testing. Is there something particular for fuzzers that makes the correlation stronger or weaker? Yeah, that's also a question that I really want to ask.
So using fuzzers solves a problem for us because we know how these test inputs are generated, and then we can make that claim over the test generating mechanism, which is the fuzzer. The claim that the fuzzer that generates the coverage is also better at bug finding. But if you look at manual generated test cases, you take the human away. You just look at the test suite. So that might introduce some threats, but that's like is part of this answer, a very small part. The bigger answer is we introduced this new idea of using agreement instead of correlation to investigate whether some measure is a good proxy measure for bug finding. And I'm also looking forward to see studies on exactly this. My intuition is we still see a strong agreement. We still see a weak agreement, or like say moderate agreement, moderate to, my intuition is we still see a strong correlation, but maybe also a moderate agreement, even for human-generated test suites.
Yeah, I wonder whether the Oracle problem might also be a big difference here, because for traditional software testing, the weakness of coverage lies in that it does not capture the test oracle power. Like if you only have test inputs, but you just skip the test assertions, you may have 100% coverage, but actually could detect no bugs because there are no oracles, right? But in fuzzing, yeah, you basically detect crash bugs, you don't need oracles. So is that one reason you think might cause the different observations?
Yeah, this might be one reason that our bug detection mechanism is our sanitizers, which automatic mechanism. So about more semantic kind of bugs, we also don't know. But my intuition would also tell me that we would see similar results, but it has to be investigated.
Yeah. Thanks. Yeah, I think it's interesting that the Oracle problem, like it's relatively weak. It's a minor, I mean, for the fuzzing community. So.
But I think you're right. So I think you can probably use the same idea to measure the strength of the oracle by varying the strength of the oracle, and then measure correlation and agreement. So the statement of so this claim whether coverage and bug finding agrees or correlates is a claim over the fuzzer, the test generating mechanism, the test suite, and the oracle.
Yeah. Thanks. So we have a question for Yinquan. Do you have an intuition how reassembling the ingredients of previous bug revealing tests lead to tests that reveal currently unfixed bugs?
Could you repeat this question?
Yeah, Marcel, just unmute yourself and explain the question.
So I like this idea that you take these ingredients and then so you look at historically failing test cases, and then you take these agreements and then ingredients and then reassemble them into hopefully failing test cases. So I'm wondering what your intuition is about why this works so well. Why can you take test cases that failed for completely different reasons and kind of reassemble them and make them fail anew? For even though the previous bugs were fixed.
Yeah, we think the historical bug revealing test program contains the complicated code logic or some corner cases that can cause JVM bugs in history JVM versions, and we take the ingredients from it and put into a new context, and we introduce some fixing strategies to make the interaction between the seed program and the ingredient stronger. So we think this should be introduced some new program state that can cause the JVM to trigger some new bugs.
Okay. So do we have more questions? I think we lost to Hao Yu. Hao Yu, are you there?
Yeah, I'm here.
Great. So I have a question for you. Because you use information retrieval to generate the assertions, and there should be some like similarity metrics in your work. Which similarity metric did you use, and why did you use it?
Okay. The evaluation metrics used in our sorry. Our overall idea for IR is to get the assertion by retrieving the most similar focal plus test method. Here we try 3 similarity metrics, including Jacquard, dice, and overlap. We find that the effectiveness of these 3 metrics are almost similar. So we finally choose one of them, Jacquard, as the retrieval approach of our IR approach. Yes.
Thank you. It's interesting that the very simple Jacquard similarity metric works very well in your scenario.
Thank you.
Yeah, I have a question for Yinquan Zhao about your history-driven test program synthesis for JVM testing. So you mentioned that you compared with the mutation-based baseline approach, right? And you detect more bugs than the baseline approach. And I think there is also the fuzzing-based approach, which the quantity of generated tests is large, but the quality is low. Because the generated tests might not compile, or for problems like that. But because it's fuzzing, the diversity and the quantity can be easily made very well. So have you compared with any fuzzing-based approach? Yeah, because it has a large quantity. So if we just imagine if we generate lots of tests and we just use those that can compile, you could still expose lots of bugs, right? So how about the comparison results with that kind of approach?
We did not compare such studies in our evaluation, but we perform similar experiments in other software systems such as the most popular tools is AFL. But we use AFL to generate a lot of test programs. These test programs are not syntactic valid. This may slow down the testing efficiency, and the results are very bad compared to our approach. And existing studies such as ClassMe and ClassFast, they have already proved that their mutation-based methods are effectiveness than the fuzzing work such as AFL. So we did not compare such tools in our evaluation.
I see. Thank you. So I have a question for Huayao Wu. So because your approach works very well and it outperforms the baseline approach in a great deal, so why do you think the baseline approach is so poor in the results?
Okay, thanks. And we have analyzed the results, and we think one possible reason is that the baseline approach, in our experiments, we consider both required and optional parameters to generate test cases. But in the previous paper of the baseline approach, they just considered the required parameters. And so in our study, we considered more parameters, and in the RESTful API testing field, a very challenging problem is to identify the valid values for these parameters. And if you don't do it carefully, it's very easy to lead to for stadio code, which is an invalid test case. And that's the main reason for we got these results. Okay.
Thanks for the answer. Any more questions? So what about you speakers? Like I had suggested, but by the PC chairs, they recommend you to read each other's paper and think about questions. Do you have any questions for each other? I think Marcel already asked questions for Yingquan. So what about other speakers?
Okay, I have a question for Yingquan. And since your approach is based on a set of historical test programs, and I'm wondering how many such programs are required to make your approach sufficiently effective?
I don't know exactly number of the test programs that are needed. In our experiments, we collect the test program from the hotspot repositories. Since I think such historical bug revision test programs are hard to obtain since they need a lot of dependencies. So we need to manually fixing the dependency issues. In our experiment, we collected 630 test programs. I'm not sure the exactly number of what the number can make our approach have a good effect, have a good experiment. I think we can conduct this experiment in the future to investigate the effect, the influence of the number of the test programs.
Okay, thanks.
Thank you.
Any more questions? So I think we still have 6 minutes. If you have any questions, just feel free to speak up.
Maybe I have one for Hua Yao. So your approach, you're generating sequences of you generate these sequences of posts messages, essentially, of messages to the API, and so I'm wondering whether you were considering some kind of feedback when you construct these sequences, because maybe a sequence of length, say 3, is already being considered as invalid, and so you don't need to construct sequences of length 4 with the same prefix. Is this something that you're interested in investigating, or?
Actually, in the our work, our method works into phase, and in this phase we construct a complete operation sequence. That is, all operations are determined in some order. And then when we try to execute this sequence, it's possible that, for example, when we executed the first 3 operations, and we cannot find possible values to execute the 4th operation. And in this case, we are trying to use some feedbacks in previous execution results to try to determine the value assignments of the following operations. Something like is a prefix operation, and then we try to expand a new operation sequence to make the testing proceed. And but basically, we do not take so much feedback information to improve our process. And it's a future work that we would like to introduce in our following studies.
Thanks. So, Gallo, if you'd like to have further discussions with Marcel, just unmute yourself, because I see that you were in active discussion in the chat window. And also any audience, please feel free to unmute yourself and just discuss with us directly.
So regarding this discussion on the fuzzers, so Marcel said something about like humans or developers. So assuming that developers design test cases intentionally to find bugs, and I wonder if this is an assumption that is true in practice, because I know people that intentionally develop test case to cover code, and so then it's again, is this? I mean, it's the same question again, but this time using humans in the loop. So I wonder whether, given a set of developers, we can measure somehow if the intention is to find bugs, to cover code, or simply to have a few test cases, more like positive testing rather than negative testing. I don't know. I think it's an interesting discussion.
Yeah, so I thought I had an intuition on this too, and it seems I don't. But it seems it's really interesting to discuss this. I mean, to evaluate this, investigate this in a study. So another thing is there's often a policy to increase coverage. So if you're developing safety critical systems, there are certain kind of standards that you have to satisfy in order to sell this product, and these standards often involve achieving 100% branch coverage, MCD coverage, or something like that. So then the question is, so then you have developers writing these test cases to satisfy these coverage goals. They are only written to satisfy these coverage goals, but not necessarily to find bugs, right? So this is another kind of perspective on human-generated test cases. Do these policies that require people to write test suites with high coverage, do these test suites that actually find bugs, versus someone who intentionally just writes test cases not to satisfy coverage criteria, but to actually find bugs? Yeah, interesting to study.
I think another problem of coverage is that, there might be some dead code, right? That during the software maintenance, like the code is dead and it could never be covered. So that's why also 100% coverage might not be a proper goal, to meet. Yeah. Yeah, I think we are good.